Mic check, check. Hello.
Okay, so this is the Holy Week. So thank you all for coming down and after Holi.
Well, why is on Friday?
Right. Yeah, yes. Okay, so we have Professor Nirmal Raj from the Indian Institute of Science, Bangalore, who is visiting us in this week. And he's been here since Monday, actually, avoided getting painted. Nirmal, welcome. The Colloquium actually is a pretty old series for the Wednesday Colloquium series. It's started with Professor Homi Bhabha, the founding director, putting this together so that all the natural sciences faculty members could get to listen to one common talk and have some discussions. So
Fantastic.
there's been a age-old thing, and there are some of the previous coordinators who are here as well. So thank you for joining in this very prestigious series, and I would request Professor Gopakumar to formally introduce Nirmal. So,
Okay, thanks.
thank you, Jody.
Thank you, JD. It's a pleasure to have Nirmal here. Nirmal is a professor at IISc in what we used to call at CTS. He's a particle theorist whose interests are in dark matter, neutrinos, gravitational waves, neutron stars, and now astronomy in detail. He graduated from Oregon, working on dark matter and supersymmetry during LSC era, then went on to do postdoc in Notre Dame and then Triumph in British Columbia. And last year he joined, IISc. And he has been kind of a regular visitor to our NPTA activities. I mean, and we keep in touch and try to entice him into our gang at some point of time. Okay, so looking forward to your talk today about the compact stars as dark matter detectors. And over to you.
Great, thank you. Thank you so much. Thanks so much, JD, and thanks for the very kind introduction, Gopu. I'm very excited to be here. Nice to see friends, old and new. And I'm very excited to give this talk. I've not given a talk of this nature. I've given department colloquia, I've given public talks, but not something in between. So let's see how it goes. I'm looking forward to it. So I wanted to share some fun stuff and results with you on things that I've been working on for 7 years now, I think, involving compact stars, dark matter, and so on. Okay, so here's like a rough map of the talk. So there are 3 ideas that we're going to synthesize here and see how they relate to each other. We're going to learn a bit about dark matter. I'm sure you've seen many talks about this, but this is my version of what dark matter is. We're going to learn a bit about dark matter, and then we're going to see what compact stars, neutron stars and white dwarfs, have to do with dark matter, what the interaction of dark matter with them could do to them, and what interesting effects come out of that. And then we're going to connect this with observation. Of course, these compact stars are out in space, so we're going to use telescopes, and what kinds of telescopes are going to give us signals for what kinds of interactions is roughly what we're going to see here. Okay. Okay, so if you were to stop me on the street and ask me to describe dark matter in 3 or 4 words, these are the words that are going to come to my mind: dark, ubiquitous, plentiful, mysterious. Right? So what do I mean by these? First of all, of course, dark matter is dark, by which I mean it is non-luminous. It does not absorb or emit or reflect light. Right? It's some substance out there that is unfriendly to photons, as faint as they come. Okay? Ubiquitous. So what we mean by ubiquitous is wherever we point our telescopes and look for gravitational anomalies, we seem to see this mysterious substance out there, invisible substance out there, on all distance scales that are larger than a few kiloparsecs. Okay, larger than the sizes of what are known as dwarf galaxies, which were formed by dark matter in the early universe. That's why the dark matter seems to be everywhere, wherever, in whatever distance scales that we are looking at. What do we mean by plentiful? It makes up 5/6 of all the mass of the universe. That is really what is most interesting about it. and it stubbornly refuses to tell us what its microscopic identity is. Okay. So how do we know it's there? Because it pulls on everything else that is visible through the force of gravity. And to illustrate this with a two-body system, the presence of some unseen mass could be inferred. And in fact, its mass can be measured by measuring the positions and velocities of masses that are swirling about it. Right? This is exactly how we discover the presence of black holes. And in fact, this is how we measure we have weighed the sun, basically. Okay. So all the evidence that we have of dark matter is gravitational in nature. That's the point I'm trying to make here. But the acknowledged pioneer of the study of dark matter is this guy, the Swiss astronomer Fritz Zwicky, who back in the 1930s looked up at the coma cluster of galaxies, and he converted the amount of light that he saw to mass, applied and measured the speeds of the galactic clusters through spectroscopy, and applied the Virial theorem and found that these galaxies in the clusters were just moving too fast. Okay, and his band-aid for that was to propose some unseen mass in the cluster. And that's where he was one of the first people to use this term, where he said, if this would be confirmed, we would get the surprising result that dark matter, Dunkelmaterie in German, is present in much greater amount than luminous matter. Okay. But like most of Zwicky's ideas, this was not taken very seriously by his astronomer colleagues. And we have to come all the way to the 1970s for things to heat up. Okay. Because in the 1970s, astronomer Vera Rubin and her colleague Kent Ford developed sophisticated spectroscopic methods and measured the rotational velocities of our galaxy and a bunch of other galaxies. And when they plotted it, as a function of the distance from the center, they found that basically the galaxies were spinning too fast. Okay, so this curve shows that if you didn't have dark matter, if you just had put in the gases and the stars, then given the mass distribution models that they had, this is the rotational velocity of these objects, which gets you a Keplerian decline. But then the data basically showed something like this. Okay, that the rotational velocity was flattening out to large distances. So that seemed to suggest that there was some missing mass, that was invisible. Okay, but even then, there was really no sense of crisis in the physics community, even after this. Okay, even though there were like 72 galaxies or something that Vera Rubin had studied, showing this, there was no real, there's not like a mystery. Not everybody was thinking about this yet. And that's because until the 1980s, if you were to ask an astronomer or an astrophysicist, what is this unseen dark matter made of, with apologies to chemists, they would point to this. Okay, and because obviously it was all just it's dark, but it's all just stuff that is too faint to see, like planets and white dwarfs and brown dwarfs and red dwarfs and black holes and neutron stars and so on. Okay, just stuff that is too faint to see, right? Except as we move into the 1990s, people started looking for these massive compact halo objects made up of these planets and neutron stars and so on in gravitational microlensing surveys, basically looking for magnification in light curves as these objects transit in your line of sight when you have some star field in the background. Okay, when people look for these in the surveys, they just came up empty-handed. Okay, and then on top of that, in the 1990s, we entered the era of precision cosmology, and in particular, we were able to measure the cosmic microwave background, the temperature anisotropies in the cosmic microwave background to better and better precision, and that suggested that seemed to suggest there was a large component of non-baryonic dark matter present in the early universe, and results from these tallied with measurements of the abundances of light elements cooked in the early universe through Big Bang nucleosynthesis, which agreed with the standard calculations. Okay, so all of this put together came to be known as the concordance model of cosmology, because they were all agreeing with each other. And you know, one of the grand conclusions of all these was that dark matter actually makes up 5/6 of all the mass of the universe. It behaves like matter cosmologically, but you know, as far as the universe is concerned, everything that we know and love in the form of atoms, stars, planets, and so on, were just a contamination. Okay, so this is when, as far as my reading of history is concerned, this is when a real sense of crisis kicked in, actually. To make matters worse or better, depending on your point of view, we were amassing even more pieces of evidence for dark matter. For instance, the large-scale structure of the universe, as inferred from astronomical surveys, was, you know, it looked very much in agreement with the large-scale structure that you would get in simulations if you put in a non-relativistic, cold, non-baryonic component of matter in the right proportions. Okay, that was very good indirect evidence for this cold dark matter. And then people started observing these clusters known as bullet clusters, in particular the bullet cluster, which is sometimes presented as in-your-face evidence for dark matter. The idea here being that you get a snapshot of two clusters that have already passed by each other. And the orange-red glow that you see here is the clusters shining in X-rays. Okay, and when people try to look at the same cluster through gravitational lensing of you know, objects that were behind this cluster in this line of sight, we got lucky about that. They were able to draw these equipotential contours, which shows that most of the mass in the system actually lies away from the cluster that you actually see in X-rays. Okay, and the only explanation for this could be that before the collision happened, the gases and the dark matter particles or whatever were all contained in you know, coexisting halos. And then as they passed through each other, the gases interacted through electromagnetism. By friction, got slowed down, and that's what we see here. Whereas the dark matter components had very little self-interactions, negligible self-interactions, and they just pass through each other. And that's why most of the mass has gone to the side.
Just a quick clarification, it's not a question.
Absolutely. Yeah.
What do you mean by cluster here? Just
cluster. By cluster, I mean
people who are outside.
Yes. By cluster, I mean a cluster of galaxies. Now we think of galaxies as particles, and these are basically clouds of galaxies. Yes, that's it. Okay, so yes, so we, depending on how you count, we have like 5 disparate pieces of evidence that dark matter does exist, and it makes up most of the mass of the matter in the universe, and that we need to think about what it is, right? Okay, so let's take a quick break here. I think I've told what I wanted to say about dark matter. The rest of the talk is going to look like this. Now I'm going to talk about how you know, the physics of the dark matter or the dark sector particles making up particles to which dark matter belongs could interact with compact stars. And then I'll be talking about, in particular, how the entities in the dark sector could heat up neutron stars and white dwarfs through what I call an external fire. And then we'll also talk about some internal fire. And then we're going to see how after you overheat these compact stars, these can be observed and constraints can be placed using a host of telescopes across the spectrum, in the infrared, optical, ultraviolet, and also by deploying some radio telescopes. Okay. All right. So let's move on to part 1 of that, which I call an external fire. Okay. So what we saw just before is that we have collected a lot of astronomical evidence for the existence of dark matter, and that this was all through the force of gravity, right? But to really know what its microscopic identity is, we need to get some sort of particle physics fingerprints of this entity, right? So, for example, you look for the scattering of the dark matter particle, or you look for some annihilation signature, etc., etc. Or you try to produce it in colliders and so on. So, some sort of particle physics fingerprint that you want that can help you start to understand what its microscopic identity could be. Is it even a particle, or is it some black hole, etc., etc. Okay. Now, one of the best tools to infer the particle physics fingerprints of an unknown entity would be scattering, right? Because scattering famously is how scattering of alpha particles on a gold foil is how Rutherford inferred the presence of a dense atomic nucleus. Scattering of X-rays is how Rosalind Franklin inferred the the double helical structure of DNA. Diffractive scattering. Okay. Sorry. Yes. So what is technically right there?
Other guys did it.
Okay. Okay. Great. Okay. And scattering of electrons and neutrinos on nucleons in the deep inelastic regime is how we inferred the presence of quarks and gluons and so on. Okay, so the historic virtues of scattering cannot be understated, and why not do a scattering experiment with dark matter as well, imagining it as a particle. Okay, so that means one can set up what I call a reverse Rutherford scattering experiment. What do I mean by that? So Rutherford knew what his beam was, but he didn't know what the target was. But in this case, we're going to imagine, we know what the target is going to be. We can set up a well-known target, and we don't know what the beam is going to be. Okay, so in that sense, it's like a reverse Rutherford scattering experiment, where the goal of this experiment would be to determine some intrinsic quantity that helps us to identify dark matter, such as the dark matter on nucleon scattering cross-section. Okay. Now, of course, the idea is that when this beam hits your target, something's going to change in your target. You might have a transfer of energy and momentum, and that could induce some light or charge or something in your target that you could study and say something about the cross section and the unknown mass of dark matter. And it turns out that you don't need many ingredients to infer limits or results from such an experiment. You need the speed of the beam, and then you need the density of the beam. Okay, and thankfully, one can have a pretty good handle on these quantities. People have been setting very good constraints on these quantities by inferring stellar motion in the solar vicinity of the galaxy. Okay, this has been being done for hundreds of years, actually, starting from Kapteyn and so on. Not hundreds of years, sorry, for 100 years, since the 1920s. Yes. It's roughly the same for both, actually.
Okay.
Not the density, sorry. For the speed. The speed is roughly the same for both dark matter and the stars, because the galaxy, you assume that the galaxy has virialized, and at a given location, everything has the same speed. Right? Okay. So the speed, the typical speed of dark matter in the solar vicinity is inferred again from stellar motion. Is it's inferred as 300 kilometers per second, which is about 1,000th the speed of light. And the density, the mass density of dark matter in units that I recognize is inferred as 0.3 GeV per centimeter cubed, which is about 2 protons per teaspoon. Okay, but it must be remembered that nobody has measured it at the centimeter cube scale. This is measured at a few 10 or 100 parsec scale. Okay, that's the coarse grain density scale at which you measure the density. Okay, so one can now think of setting up such a reverse Rutherford experiment. By the way, I don't think I have a slide on this. Let me just say one thing quickly. An experiment like this, experiments like these are already being done in underground detectors, okay, in controlled laboratory conditions. And this goes by the name of direct detection, but that's not what I'm going to be talking about today. Okay, but one can take the philosophy of these kinds of scattering experiments and think of a different kind of detector, which I propose would an ideal candidate would be a neutron star, right? So what is a neutron star? This is a degenerate remnant left behind by a core collapse supernova, right? And made up of basically mostly neutrons, but then due to beta equilibrium, you also you would also have a bunch of protons and electrons and muons and so on. Okay. So neutron stars and white dwarfs, which are their degenerate cousins, have been recognized as excellent detectors of dark matter. For the last couple of decades or so, people have been working on this. And I've been fascinated by this subject. My frequent collaborator, Joe Bramante, has been fascinated by it. And then we decided to just write a review about it, compiling all the literature on the subject of using, compact stars as dark matter detectors. And if anybody is interested, I encourage you to go and look at this. We hope to have been comprehensive and covered all the literature on this. Okay. Now that we are imagining neutron stars as our reverse Rutherford detectors, let's think about some of the properties of this detector. The neutron star spans about 20 kilometers, which is about a half marathon, which is very large for a particle detector, but psychotically tiny for a star, right? And the cores of neutron stars are some of the densest objects known to humans, right? And their densities are known to exceed nuclear saturation densities and range in 10 power 15 grams per centimeter cube. Okay, and finally, standard cooling theories tell you that neutron stars, given enough time, if they're older than about 200 million years old, they would cool down to basically thousands of Kelvin. And then if you wait a little longer, they even cool down all the way to 100 Kelvin or so. Okay, so people generally talk about neutron stars as giant nuclei in the sky, but most neutron stars are also giant snowballs in the sky, literally, right? Because this is the temperature of a snowball. Okay, so with these properties, myself and a bunch of collaborators had proposed a simple mechanism by which dark matter in just one step could overheat these detectors. And you can, by looking for this overheating, you can infer the presence of dark matter interactions. Okay, so that's what this paper is about. And the idea is that the ambient, all the ambient dark matter around the neutron star, this cartoon doesn't do justice. In this cartoon, I'm showing a single dark matter particle, but please imagine a bunch of dark matter particles all around it. All the dark matter particles around the neutron star get accelerated in the steep gravitational potential of this very dense object, falls into the neutron star, and if there are scattering interactions, then the kinetic energy, the enhanced kinetic energy now of the dark matter gets transferred to the neutron star, right? And under thermal equilibrium conditions, the heating rate through this mechanism will be equal to the cooling rate. In other words, the luminosity of the star that I'm measuring, the photon luminosity, should be equal to the kinetic power. Okay, that's the mechanism. That's all that we proposed. There were other mechanisms that were in the literature before, but then we simplified it and we showed that this is all that you need to heat up a neutron star. Now, there's an exact analogy to this, which is, how do you keep a bowl of soup hot? You first heat it up, but then if you let it go, it's going to cool down. And if you model it as a black body, the cooling rate goes as 4 powers of the temperature. Yes, please.
Gas. You have a gas of dark matter particles.
Yes.
Moving at whatever galactic velocities.
Yes.
300. So is that small enough to produce a accretion disk around the star or not?
It actually will start forming an accretion disk in the beginning. Yes, the gas will, but it's a very dilute accretion disk.
Right. So then I should think about the accretion disk leaking into the star, right?
That's right.
Yeah.
Exactly.
That's
That's
the
absolutely right. That's
calculation that-
exactly how this calculation goes. Absolutely. Absolutely. There's an accretion disk and then it scatters again and again and then slowly shrinks into the star. But there's always an accretion disk because there's always dark matter particles. Absolutely. Thanks. Yes, yes, please.
How are you thinking, I mean, assuming the distribution of dark matter particle, is it uniform? I mean, how are you assuming the gas?
Fantastic question. The general assumption is it is uniform. We will see what happens if it is non-uniform. I have a slide on that as well. That is, we generally assume it's a homogeneously, smoothly distributed gas, and then the neutron star is just sitting in that bath, and then things are accreting. But if the dark matter is clumped, we'll see what happens. We have a different signature for that. Excellent, thanks. Okay, so the soup, the bowl of soup would keep cooling, but if you want to maintain the temperature, that is, if you want to set the left-hand side to 0, I turn on an external power source, right? Which in this case is a fire, which transfers kinetic energy to the molecules in the soup. That's just what I'm doing here. Instead of a fire made up of standard model particles, I have a fire made up of dark matter particles, basically. That's the idea here. Okay. Okay. Now, the problem that I just set up in my mind is actually so simple that Zwicky himself could have done this calculation. Okay. So in Zwicky's time, from Kapteyn's measurement, he knew the density of dark matter. He could have inferred the speed of dark matter in the solar vicinity. And so, in 1933, he proposed the existence of dark matter. And then the very next year, he proposed the existence of neutron stars as well, supernovae and neutron stars. So actually, he could have done this calculation. He just had to know the kinetic energy of dark matter falling in, the number of flux and so on, which he could get from these numbers. And, set up black body temperature, black body luminosity, and he could have answered the question, how hot can my dark matter keep my neutron star? He could have answered it himself and discovered dark matter through neutron stars and neutron stars through dark matter, actually. But, okay, yes. Yes.
They do get an inherent kick. Usually, some of them can go to 1,000 kilometers per second.
Correct.
Will that be aiding your efforts, or it will be?
It will not particularly aid this. It will actually reduce the luminosity a bit.
Okay.
Because the relative velocity, overall the relative velocity actually has become larger.
Mhm.
And that will actually not aid me. I need the relative velocity to be smaller for me to get some enhancement in the flux.
Yeah.
So my field
And
enhancement.
also the fact that it's moving and getting slowed down in the galactic potential
Right.
creates other complications. So
Indeed.
Okay.
So that refinement has been, so I didn't do it. One of my colleagues, Raghuvir Garani, and in fact, Sudhir Vempati and Rajiv, they did this refinement actually. I don't know if I have a plot on it, but they did put in the neutron star velocity distribution and saw that the luminosity was going down a little bit, but not enough to damage the story actually. Yes.
So if the relative velocity is larger, the flux falling on neutron star is larger, right?
It's actually smaller, it turns out, because so when the flux falls in, it gets a gravitational focusing effect, actually. So,
Okay.
so the flux gets multiplied by a V escape squared over V squared. So, yes.
How large dark matter
Yes.
do you consider? Because if it is too heavy, it will already cause oscillations on the surface of the neutron star.
If the cross section is too high, it will do that.
Or even it's heavier, but it can really do a damage to the neutron star by creating.
That is also true. Yes,
How large
that's right.
mass? What is the boundary?
For me, the boundary can go all the way to 10 power 30 GeV or so. So the effect that you're talking about, you need the dark matter to be like a macroscopic thing for it to actually hit it and disintegrate the star.
Cause additional modes on the surface of the.
Correct. Because additional, yes, tidal heating and all that. Yes, tidal modes. So that happens at very large masses.
So it's not possible. It's not possible to do that because there's this gravitational focusing, right? So
No,
can you use that to
for tidal deformations?
Yeah.
That actually enhances the tidal deformations actually, because we have more flux coming in. And
So that's what I said. Instead of going to high mass, can you toward the mass.
Right. So the numbers that I mentioned already accounts for this already. So what? Just to be clear, just without thinking of numbers, the story I'm saying here is where you can think of dark matter as elementary particles. Roughly from a GeV, TeV, even up to a Planck mass. For these things to happen, we're not thinking of particles anymore. We're thinking of composite particles. Think of dark matter meteors and things like that. So that's the separation.
Particle dark matter.
Yeah, particle dark matter can't do this. Exactly. Yeah. At this point, it's still a gas that's falling. Yes.
And so, I mean, there are limits, right? Lab limits.
Yes. Yes, I will show the underground detection limit. So I'll show how these two complement each other. Okay. So now just to round up the astrophysics part, now this heating mechanism, oh dear, I missed a slide somewhere here, sorry. So I think I missed something here, that through this heating mechanism, roughly the maximum temperature that you can impart to neutron stars is about 2000 Kelvin. Okay, for a certain benchmark star, I found it was 1750 Kelvin, but it's roughly, given the variations in masses and radii, it's about 2000 Kelvin. Because there is a limitation to how much energy you can transfer, coming from the limitation in the velocity and the density of dark matter, the ambient density of dark matter, right? World loss, you heat it up by like 30 Kelvin or so, actually. The energy flux is too small. So through this mechanism, at least. Okay, so the slide I forgot to put in was that the coldest neutron star that we have observed is at around 40,000 Kelvin. And we've not even observed it. We've only set an upper limit on its temperature, but that's 40,000 Kelvin, which is like a factor of 20 above the temperature that I'm imparting to the neutron star, right? No, this is not even, this is a nearby pulsar seen through HST, actually. The Magnificent 7 is 10 times more hotter than even that, actually. Okay, so then what do you do? Then there's no real limits that you can set today. So what can we really do with this mechanism? There's something cute going on here, but can we really observe it? And we've been breaking our head over this for some time. And what this seems to us as one of the reasonable trajectories that we could take to connect this with observation. The trajectory goes like this. First, you discover these neutron stars as pulsars, okay? Pulsars being, neutron stars that emit electromagnetic radiation from their poles, and as they rotate in your line of sight, the jets sweep across you like a lighthouse in very regular pulses. Okay, so discover them as pulsars in radio telescopes such as CHIME and FAST, and these are putting out discoveries by the day, basically, of neutron stars. And then find some candidate neutron stars. And for reference, it's believed that within the local 50 parsecs of Earth, there are some 100 cold, old, isolated neutron stars around. Okay, that have not been discovered yet. So, if some of these were discovered by these radio telescopes, then we know exactly where they are in the sky. Remember that these are psychotically tiny stars, right? So we need to know exactly where they are, and then we can ask. The James Webb Space Telescope, launched a couple of years ago, or the extremely large telescope coming up next year, or the 30-meter telescope that will very hopefully come up in a few years. These telescopes operate in the right temperature range, so that we can ask right wavelength range, so that we can ask them to point at these neutron stars and make a statement about how hot these neutron stars are. Okay, so that's the general idea. Now, I'm going to take a 3-slide digression on this part of the story, where I want to tell a sub-story about using telescopes and compact stars without reference to dark matter. I know dark matter is the heart of the talk, but this can be, we discovered something interesting, that there is a story here even without reference to dark matter. Okay, which is that before us, as far as we could tell, nobody has written a proposal to measure neutron star temperatures using these telescopes. Okay, no dark matter story, nothing. So as a standalone astronomical project, there was something to do, and the project was, interesting but simple enough. that I was able to actually do this with a couple of undergrads at IISc, pretty motivated undergrads, Prajwal and Gaurav. And basically the title, this paper just came out this month. The paper talks about sub 40,000 Kelvin neutron stars. Why sub 40,000 Kelvin? The coldest one, is around 3 or 4, 30,000 or 40,000 Kelvin with an upper limit. And the coldest actually measured pulsar is at 10 power 5 Kelvin and so on. So that's a good upper range. And the way we pitched it is to say that, there are so many late time reheating mechanisms out there in the astrophysics literature, in the fundamental physics literature, things like rotochemical, vortex creep, crust tracking. I don't want to talk about all this now, but there are many nice mechanisms out there in literature that might heat up neutron stars in their late times. In that case, it becomes important to really measure the temperature. Basically use your telescopes like JWST and TMT and ELT as thermometers, because these are the most sensitive thermometers we have of neutron stars today. So just measure the temperature, and then we can think about the physics implications of that. Okay, and these plots basically show that this can be done if I put a neutron star at 30 parsecs distance, which is not very crazy, and if it's glowing at 4,000 Kelvin, then the spectral flux density that I get will be covered by a lot of filters on the James Webb, JWST, right, which is imaging instrument. And similarly, if I put a neutron star at 100 parsecs away and I make it glow at 40,000 Kelvin, the ELT can catch it very handsomely. Yes. No. Yes. Exactly. Yes, this is optical and that's infrared. Absolutely. Yes. Something is reheating them. That is assumption here. Yes, it's a pure thermal spectrum. And that's generally a good enough assumption in astronomy for late time neutron stars, at least. This one is right. So these are the black body spectral flux densities. And then these are
optical pulsar. Should you agree with that?
But no, I'm not thinking of the pulsation. The pulsation is still in radio, but yes. Yeah, but the thermal emission is in optical.
It's black body.
It is a black body. Yes, absolutely. Right. Tuhin, you had a question. The red one is the spectral flux density. You take a black body spectrum and divide by 4 pi d squared. So the blue ones are the filter sensitivities of these. Exactly. Yes. And then we made plots like these where we show that, for a 40,000 Kelvin pulsar, if with these different filters in JWST, ELT, and TMT, I can measure the temperature of this pulsar, or I can set a constraint on the temperature of this pulsar as long as it's within, say, 550 parsecs for this filter, or 500 parsecs or something for this filter, and so on. Okay. That will be yes. Yes, absolutely, yes. Although that doesn't stop people. I think there's already been a search there. That didn't stop people from looking at it through with JWST anyway to look for some non-thermal component. So yes, that game can always be played. Cassiopeia A has also been looked at. And similarly for 2000 Kelvin neutron star, as long as it's within a few tens of parsecs, then I can set a limit on it. That's the idea. So on the right hand y-axis, we are also showing the number of neutron stars that you expect within this the spherical volume of this distance. Okay, so over here you have up to 10 power 5 neutron stars to play with. 10 power 5 seems like an exciting number, but we've only discovered around 4,000 neutron stars. There's a big selection bias going on here because you need neutron stars to pulsate or do something different to catch them. But there are many neutron stars that we just haven't seen. Okay, but hopefully we'll catch them. We'll catch some fraction of them and see them. We don't need pulses anyway. Yes.
There's a survey.
Exactly. Absolutely. Yeah. If that is one of the spectacular signals that may happen if for all the neutron stars, there is some reheating mechanism. Let's not say dark matter. Something is reheating neutron stars. And if actually all these old neutron stars are glowing at say 20,000 Kelvin, then if you have an infrared or an optical survey, a deep field survey, then all of a sudden you'll be seeing in your field of view like 10 power 4 neutron stars that are glowing, or 10 power 4 point sources basically. That's the idea. Nobody has done this yet. So, okay.
In temperature, what is the reach of the telescope?
Right. So it depends exactly on what we mean by temperature. On the x-axis up here, I'm indicating the black body peak temperature corresponding to the central wavelength of that filter. So in that sense, the JWST is touted to be, it ranges between infrared and orange. This is around orange actually. That's the peak one. But then I can catch it beyond the peak also. I can catch the
Right.
spectral flux.
But that means that you don't have to go to 10, 20,000. You take a deep field,
Yes.
1500 or something.
Okay, correct. Yes, agreed. Even with an infrared survey telescope, I can catch it. Agreed. Yes.
I was just wondering, how do you make this calculation about the number of neutron star within the solar neighborhood? So you start with the initial mass function about some mass will go off as called core collapse supernovae and end up as
Exactly.
neutron
That's
star
exactly-
over the last 12 billion years. Is that the?
Indeed. That's exactly how people, take the initial mass function. And then people either assume constant supernova rate or a higher supernova rate in the past. So there is some uncertainty
Yeah,
on
there
that.
is strong metallicity dependence and all that, right?
Right.
So that number is highly uncertain.
So that number is, so there is an uncertainty of a factor of 5 either way on this actually. So yes, definitely. So this, I didn't put it on the plot, but it's in the paper. Yes. I was using Sartore and Ofek, who did some simulations and all that using this.
Just one quick question, then we will give you the full time.
Okay, that's totally, no, this is great.
Just a quick question, Abhi.
Yes.
What is the time scale over which the temperature increases you're talking about? So the reheating time scale.
So the word reheating is a bit misleading. So we actually wrote this in the paper also, saying this is not really reheating, although that's the word being used, so we had to use. So nothing is getting reheated here. There's always been an input of energy, but we never saw this when the pulsar is young, when the neutron star is young, we don't see this input. But you need to wait for it to cool down to a natural luminosity below this heating luminosity, and then you see that the light curve bottom. Yeah, exactly. Saturates.
So the question is how
Yeah.
old
How old should you get? Okay. That depends on the temperature. I don't have a cooling curve, but for 20,000, 40,000 Kelvin, I need to wait about 1 million years. And then for 1,000 Kelvin, I need to wait 200 million years, basically. Yeah, that's and then the nice thing is the older neutron stars are more populous anyway. The weightage goes as the age of the neutron star. So.
Please proceed.
Okay, great.
Finish the talk.
Okay, great. Okay, fantastic. Okay. Okay, so just one very quick thing before I go to the next one, before I go back to dark matter. One exciting thing we found while doing this project is that this pulsar, the coldest neutron star measured at around 40,000 Kelvin, using the JWST, we could already push down on the temperature measurement of this down to about 20,000 Kelvin. And then with ELT, we can go to 15,000 Kelvin. With TMT, we can go to 10,000 Kelvin. So already we have the means to remeasure, push down the neutron star temperature frontier, which will have implications for astrophysical reheating mechanisms. Okay, so these are some catalogs. We measured we estimated the distances to some pulsars in catalogs from CHIME and FAST and so on. Okay. Anyway, so back to dark matter. So as a particle physicist, you want to ask, okay, nice, you can reheat neutron stars in their late stage with the flux of particle dark matter falling in, but what does it really imply for fundamental parameters, right? Like the Lagrangian couplings and so on. And one place where you can start answering that question is planes like these in the cross section for dark matter hitting nucleons, versus the unknown mass of dark matter. Okay, this is a plane, for instance, in which these underground experiments display their results, their constraints. And notice that over here, the cross sections vary over 40 orders of magnitude, which is the range over which terrestrial experiments are able to set their limits, and the mass ranges over 20 orders of magnitude, which is roughly where you expect the dark matter to behave like a particle in your detector. Okay. And the answer looks like this. Okay. So all these weird shapes, these are limits from experiments underground, on the surface of the Earth, balloons, rockets, satellites, and so on. Okay, so all the space enclosed by these weird quadrilaterals. Okay. On top of that, I have superimposed the cross sections and masses that can be constrained using a neutron star that's glowing at around 2000 Kelvin. Okay, so as long as you are above this cross section for a certain mass, you will deposit all the kinetic energy. The dark matter will deposit all the kinetic energy and raise your neutron star. Yes.
The maximum temperature that you can get for the neutron star, is it not a function of mass?
No.
Kinetic energy of dark matter particles.
Right. So yeah, that's a good point. So exactly, they balance each other. Exactly. So as you increase the mass, the number density goes as 1 over the mass, and but the kinetic energy goes as the mass, so they balance each other. The reason you start losing sensitivity here, so that idea is encapsulated by this straight line, basically, that there's no cross-section sensitivity, but you lose sensitivity at high masses because at high enough masses, the kinetic energy is so large that it takes multiple scatters to deposit energy to get captured in the star, to deposit all the energy, basically. Okay. So as you can immediately see visually here, just on this plane, a search with neutron stars, even at the maximal temperature, would be very complementary to dark matter direct detection, especially at low masses. Even at high masses, there is actually no constraint over here. These are future constraints, future reaches. So just with this, you can.
Taken a standard some EFT for dark matter.
That's right. Yes.
The usual.
The usual. Yeah, exactly. Contact interactions. Yes. And if I were to look at colder and colder neutron stars, I can push this boundary down proportionally. Right? Okay. Okay. So let me quickly run through some variations, on this theme that I had been exploring. For instance, should the dark matter really thermalize with the neutron star if we have to see its effects? What I mean by that is, does the dark matter distribution inside the neutron star after it is captured, does it look like this or this? And that's a very model dependent question, because depending on the scattering nature, you might repeatedly scatter efficiently and then gather all the way down to this little ball. And then again, depending on the model, the dark matter in this tightly bound ball could annihilate efficiently. And if the final state products are standard model particles, then I'll be depositing some more energy, the mass energy of the dark matter also, into the star. And that will raise the luminosity of the star or the temperature of the star and help save telescope time, or help you choose the right filter and so on. Okay, but it's a very model dependent question. So that's what we had investigated. And as I was saying, a neutron star doesn't, it's a misnomer. It doesn't contain just neutrons. It also has to contain at the least protons, electrons, and muons because of beta equilibrium. And that means, one can think of dark matter that exclusively scatters with only electrons or muons or protons and so on. So this has to be treated carefully, putting in the correct kinematics and so on. And that was one of the studies that we had done. One other fun exploration we had done was, maybe you shouldn't even think about the core of the neutron star consisting of neutrons, because yes.
But finally, depends a lot the kind of interaction that you're taking, whether it is doing elastic scattering or an inelastic.
Absolutely.
But it's a huge collection of protons and neutrons, as you were saying.
Yes.
Fundamental interaction gives you order one difference between what effect you get at the end of the day.
Correct.
How are you drawing those simplistic curves?
Which one? Which,
Before.
the one before?
Yeah.
This is, the assumption baked into this is elastic contact interactions. So I mean, just like, these curves, if you take the xenon one-ton curve, for instance,
The proton talks in the same manner as a neutron.
that's right. In this
And
case,
the entire effect of it just sums over like a number.
you could say that, yes. But the proton population is anyway so small that it won't really affect the curve here in this case, unlike in a direct direction experiment. Yes. Yes, so that's why. So this is like the first thing that you would think about, and then there are more variations. So people have thought about all these: velocity dependent, inelastic, spin dependent, etc., electron scattering, etc., 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 etc. Right.
Does
So
it not matter the density of the dark matter locally around the vicinity of your
yes, it matters. We are just taking it as 0.3 GeV per centimeter cube.
that's the thing.
That it does, yes, absolutely, absolutely. So there's 100% uncertainty on the luminosity as well. That is a very valid point. Yes, exactly. But still doesn't matter because the broader story is that you get it to the roughly the yeah, exactly, yeah. Okay, so very quickly here, to be very honest, the composition of the inner core of the neutron star, which makes up most of the volume of the star, by the way, is not completely known because the state of matter at these very high densities, above nuclear saturation densities, is not completely known. So it's not very clear what governs the dynamics of dark matter scattering with these objects. Maybe the core doesn't even contain neutrons. It may contain strange matter, hyperons. Did I have that? No. Yeah, it could be made of quark matter and meson conditions. Sorry?
So that
yes, exactly. So to the simple EFT, it won't really make a difference. It won't make a qualitative difference. But just in case there is a very crazy dark matter model out there that doesn't particularly have appreciable interactions with matter like this, one can imagine setting limits on scattering with just the crust alone, because the crust is much better understood than the core. Okay, these are at much smaller densities. So that was one of the variations that we had explored. Here's a cross section of the crust. I don't want to go into the details again, but I just want to say that the deeper you go into the crust, the knowledge of the structure becomes more uncertain. So one can take scattering at the top of the crust more seriously than scattering at the bottom of the crust. Okay. Yes. Okay. Okay, so we got some sensitivities out of that as well. And one final variation is something that you had mentioned. What if dark matter is not smoothly distributed in the galactic halo, but comes in the form of clumps? This is not such a crazy idea because a lot of non-standard cosmologies do predict a lot of population boost in the form of dark matter sitting in clumps. Okay, in that case, one can think of a nightmare scenario for underground detection, where since the inception of these experiments in the 1970s, the Earth has never encountered a dark matter clump. So we've been waiting for decades for dark matter to scatter, but maybe there was never a dark matter particle that ever passed through the Earth anyway, in the form of a clump, sitting in a clump, right? In that case, what do you do? What if dark matter has scattering interactions with nucleons anyway? Well, neutron stars can come to our rescue, because once in a while neutron stars can encounter these clumps, sometimes called subhalos, microhalos, and so on in the literature. And one can calculate the encounter rate, the energy transfer rate, and so on, and show limits on the plane of the size of the clump versus the mass of the clump. And we find that there is some parameter space where you still heat up the neutron star, like I had talked about before, if the encounters are fast enough. But even if the encounters are rare, you heat up the neutron star temporarily, but it takes a long time to cool down, so that there's always a fraction of neutron stars in a given population that's above some predicted temperature. So you look for them in sky surveys and so on. Okay. So there's all sorts of games one can play, imagining different things on neutron stars, different things in the constituents of neutron stars, and different things about dark matter. Okay. And one other fun thing that can come out of this is, if dark matter was a macroscopic particle, like you were mentioning, not really an elementary particle, ranging in masses of grams or thousands of grams or even much heavier than that, then these composite states could strike white dwarfs as they transit through them, and then could deposit enough energy in a small pocket of the white dwarf. And as long as you deposit enough energy to increase it to some critical temperature to initiate nuclear fusion, runaway nuclear fusion, and as long as the rate at which you're depositing the energy is larger than the rate at which it's cooling down due to diffusion, then you will set up a chain reaction, and you basically have created a type 1a supernova. Okay, so you can explode white dwarfs. Also this way, you can also explode the crusts of neutron stars, which are thought to contain carbon. You get what are known as superbursts. This was an idea actually triggered by interactions with Gopu last year at IMSC. He told me to go look at low mass X-ray binaries, and then this is what came out of this. So you can have these X-ray fountains, and by monitoring these, one can set pretty interesting limits on dark matter sizes. Yeah, what is ruled out?
None of this is none of the phase space available.
So this is the part that's ruled out. Actually. The space inside these triangles basically is ruled out because of the type 1a bursts. Yes. Yes, exactly. You need macroscopic dark matter to do this. Particles won't just cut it. Yes. You need to deposit grams of energy basically to do this. 10 power 57. So yeah, or a gram is 10 power 24 G. Okay. So how much time do I have left? 5 to 10 minutes, I'll wrap up. Okay, that sounds good. Okay. So coming to the next part, which is an internal fire. This doesn't have to do with dark matter as such, but maybe with friends of dark matter. Okay. So what do I mean by internal fire? Let's see how quickly I can do this. This pertains to a very specific model of some hidden sector which could make up dark matter. Okay. Previously, I was talking about something that was mostly model agnostic. Many models could be friendly to the signature I was talking about there, but this happens only in very specific models. In particular, we are thinking of hypothetical particles that are known as dark neutrons. What are they? They are characterized by they're neutral under all fundamental forces. They have a spin half, and they have a baryon number 1. Okay, if I just characterize it this way, then the disgruntled ghost of James Chadwick is going to come up and tell me I've just described a neutron, right? And of course, there are other flavor variations of that as well, right? And James Chadwick wouldn't be completely wrong because, I have described a neutron, but I just haven't specified its mass, okay? And so this exotic particle, that's exactly why people call them dark neutrons or hidden neutrons, sometimes mirror neutrons and so on. In that case, I can always set up two Hamiltonian with the two particles, and there's nothing that forbids me from having an off-diagonal mass in the Hamiltonian, which would lead to quantum mixing between these two states. Quantum mixing is not something exotic. We see many examples of it in nature. The photon mixes with the rho meson at higher energies. It also appreciably mixes with the Z boson. The neutrino flavors mix with each other, famously telling us that that's how we know that neutrinos have mass, and so on. So that's what we are having, neutrons mixing with dark neutrons, which could lead to oscillations in the probability of detection of these neutrons or dark neutrons, so that you can actually shine a neutron through a wall. Okay, you can convert to a dark neutron when it encounters a wall and come back to the other side. Okay, so why do we want to care? There are many reasons people think about dark neutrons, but for this talk we care because the dark neutron could be a long-lived state. It's electrically neutral, so it could be the dark matter of the universe. Okay, and when you do some standard cosmology calculations, you find that the dark neutron abundance is comparable to the baryon abundance, which is what we expect most of the, which is what I expect from dark matter anyway. Yes.
So how is it exactly stable?
It could be lighter.
How?
That's, yeah. So, okay,
Mass difference is pretty, it's well understood.
that's right. That's right. So it has to be, yeah. So you had asked me this last time also. So it has to be within like 1.3 MeV of the neutron mass for this to happen. Though I'll show you an exception to that also. Yes. Okay.
0.3 MeV is just too much this.
No, yeah, the proton neutron mass difference is 1.3 MeV. And
very small.
correct. So yes. All I'm saying is it has to be, why do you say it has to be very small? No. It has to be between, the mass has to be above the proton mass, but below the neutron mass. Because
No, that's not what I'm saying.
Ha.
The mass difference between proton and neutron is well understood.
Yes.
In terms of there is it's a mu minus mu dependence, that is the electromagnetic factor.
Okay.
Proton
Understood in
Okay.
Mu minus mu dependence shows up in the pion spectroscopy, right?
Yes.
So from there, we actually put together, and that part is pretty well. It's a
Very good.
physical thing. No?
Very
So
good.
when you write out diagonal piece, you are also going to split the Mn from the original value. Right? So it's
No.
going to be additional factor.
No. So the eigenmass that I get, yeah, the eigenmass that I get, I'm still going to call that the neutron that we have measured. Actually. Yes.
But let's understand the origin of neutron mass, the number that is given proton mass.
Okay.
Right? So it's not just different. We understand what neutron mass is in standard.
Okay.
So now if you now calculate it, you
Yes.
have the predicted mass from standard model minus your epsilon square over the difference of.
Yes. So that's a good point. But let me just say one thing here. These epsilons that I'm thinking of are 10 power minus 6 electron volts and so on. So it's, yeah, it's very, very fine. So yes. Okay.
Why that?
Hmm?
You did
So-
not consider this.
Okay.
Why did you take it? 6?
One doesn't have to, but at higher epsilons, I run into terrible constraints from BBN and yes, terrestrial structures and so on. Yeah. Okay, so what does this have to do with neutron stars? Okay, when I say neutron stars, this is probably the image that you get. Giant nucleus in the sky and possibly some pulsating mechanism through jets from the poles, right? And then, it's not just the nucleus consists of 10 power 57 neutrons and a 10% smattering of protons, electrons, and muons, as we just saw. But if you stare at it longer, we'll also think of another image in energy space, right? That the nucleons and the electrons also are distributed as a Fermi gas, right? In discrete energy levels. With a Fermi surface that's around 100 MeV, a few hundreds of them. Okay, the nucleons and electrons basically form a Fermi sea, right? Now, if I had processes going on in the neutron star where I remove a neutron from the Fermi sea, okay, either through decay or through scattering with some spectator nucleon, and in particular, if I convert to a dark neutron this way, if I remove a level from the Fermi sea, then the levels above it are gonna, they're gonna try to fill this hole. Nature abhors holes, as we know, right? Physically, the surrounding nucleons will rush to fill in the vacancy left behind by the neutron. In that process, there will be a frenzy of spillage of electromagnetic and kinetic energy. And given that there are 10 power 57 neutrons and 10 power 56 protons, this would basically lead to an explosive liberation of energy all over the star.
Take this two-state thing.
Mm-hmm.
Okay, that's whatever makes sense.
Mm-hmm.
One of the eigenstates, one of the mass eigenstates, you call it the neutron.
Yes,
The other is
a dark neutron. Yes.
So there's no other interaction. They cannot be this interaction.
You're saying they cannot be.
What is a neutron?
Yes.
They have already taken care of this.
No. So I don't understand. No.
They're quantum states.
Yes.
of each particle.
Correct.
Okay, that's what Fermi is. Right.
Fine. Yes.
Now, there are interactions between what you call N and chi.
Yes. No, not an N chi.
In prime and chi prime.
The interaction is only between N and N, actually. I mean, it's nucleon scattering, which gives me fine. So I don't, yes. There is no chi that I'm interacting with. There is no chi surrounding. The nucleons see the other nucleons and convert to a chi. That is the idea.
If there's a neutron chi mixing
Yes.
and neutron prime mixing, and the physical neutron is an eigenstate of mass.
Yes.
The physical chi is a different eigenstate of mass. Then any neutron scattering cannot couple.
No, that is not true, actually. Yes. Yes, we can. Yes.
Maybe that's.
Yeah, I'll go to my, I'll just finish now. Yeah, we can talk about this. Okay. So the punchline is there will be an explosive liberation of energy again. That's the internal fire that I was talking about. And then once again, you can slap this on to, the telescope story. Okay. And look for the overheating of neutron stars. And you get a bunch of constraints that in large part of parameter space beats constraints from terrestrial experiments. Okay. So let me just re-summarize again. We saw some external fire mechanisms with dark matter that is smoothly distributed, dark matter that is distributed as clumps. We also saw internal fire through what I term the nucleon or J effect by creating holes in the Fermi sea, and overheating of compact stars can be observed in a bevy of telescopes. So I always flash this slide at the end of my talks. My hope is always that, with all these people thinking very hard about this problem, maybe in the near future, dark matter will remain dark, ubiquitous, and plentiful, but hopefully not mysterious, and we'll learn something fun about the universe that we live in. Thank you.
Thank you very much.
It was a very nice colloquium, and it generated a lot of questions and interaction. That's how typically the colloquium should be. So thank you. Here's a question.
So you mentioned in your last slide.
Yes.
That the Fermi battery where you mentioned this 100 MeV energy difference in the.
Yes. This one.
So as I understand that on the crust of the neutron star, you have neutron-rich nuclei. And there, when you have interactions, the energy levels are much smaller. The energy difference between the levels may be much smaller. So then, see, if you have finite nuclei on the crust of the neutron star,
Yes.
there, if you have scattering with the dark matter, then the excitation energies may be much smaller.
Yes.
But
So
how that is going to affect your this picture?
Okay. So if I understand correctly, you are talking, if we take this picture and then we are taking the first scenario where the dark matter is scattering, the energy excitation won't, you're saying it may not probably kick you above the Fermi sea.
Much smaller.
Excellent. Okay. So that is known as polyblocking. And the plot that I had shown here, this plot, for masses above about a GeV, the recoil energy is actually GeV also. Because now we have to imagine the dark matter falling in almost close to the speed of light through the gravitational potential. So the recoil energy is above a GeV. The reason I lose sensitivity here below a GeV is exactly this effect, the polyblocking effect, where the dark matter is light, the recoil energy I'm giving is also light, so I cannot kick, there's only a fraction of neutrons near the surface that I can kick above the Fermi sea, and that suppresses my sensitivity over.
Okay. Just here, wait. Kajuri has not asked.
Same slide.
Yes.
And then going to.
Same slide. Okay.
Now, maybe I didn't understand things. Is there that n going to chi plus anything?
Yes. Although it turns out that is not such an important process compared to the rate for that is.
You do the baryon number violation.
No, the chi carries baryon number. Yes. And in this particular model that I was showing, anything is actually a photon. It's n going to chi photon.
Chi carries baryon number.
Yeah.
Okay. Sure. Wait, I'm coming. Yeah, okay. Yeah.
Yeah, nobody is online, so.
Okay.
Oh. Okay.
So maybe I have missed
Yes,
something.
yes.
So you said that the expected effect of dark matter accretion onto the temperature of the neutron star is at the level of roughly 1750 Kelvin. You said, let's call it 2000 Kelvin.
Yes, yes.
Then using the bigger telescopes that are upcoming or JWST,
Yes.
the sensitivity of the nearby pulsars / neutron stars you said are of order 20,000 Kelvin-ish.
That's right. Yeah.
So isn't that like 2 orders of magnitude too low?
No, that's not the sensitivity. You can also catch 2000 Kelvin neutron stars, actually. So 20,000 is not the limit, actually. You can do 20,000 also. 20,000 is much better. But so that is why I try to like to phrase this in the language of maximum distance of the neutron star that you can make a
No,
measurement.
so the best possible scenario is
Yes.
very close, very old, very cold neutron star.
Yes.
That is not going below 2000 Kelvin.
Correct.
Okay.
Yes.
So the biggest problem in neutron stars, so you also said that the typical ages of neutron
Yes.
star that start become
Yes.
interesting is a few hundred million years.
Okay. Yes. I want to be older than a few hundred million years. Yes.
Let's call it a gigayear.
Yes.
Okay. So so let's say that you detect a large number of gigayear-old neutron stars.
Yes.
Okay. Then how do you measure the the age so well that you can predict what
Right.
the
Very good.
without dark matter temperature should be
Very good. Yes.
at a
yes.
precision of only 2000 Kelvin
Right.
to say something about dark matter?
Right. Very
creating?
good. So, yes. So, in the interest of time, I had omitted saying one thing. This also, to really nail this, one has to have an independent measurement of age, and that is what is known as spin down age. That is, if you after you discover a pulsar, you measure the period, and then you also measure the rate at which the period is slowing down. And these two quantities give you a very good ballpark of what the age is. It gives you the correct order of magnitude at least.
Yes, it's recycled.
Yeah, yeah. How do I know what? So what? Say that again. What?
This formula.
Yes. How do I know it works for that?
Yes,
Why
because we
should it
haven't
not?
detected any.
I ask you back, why should it not work for that? So, see, think about where did the formula come from? Yes.
Right.
The dipole radiation actually removes the
Mhm.
rotational energy.
Okay,
And that is where that comes from. And as long as that is not affected, and I'm thinking of old isolated neutron stars anyway. There's no accretion or anything.
Okay.
happening. So,
Okay.
I think it'll be very hard, but it'll be fantastic if you
yeah,
could do
I
it.
know it's very challenging. Yes.
Yeah. No, so the idea is that SK is supposed to get something like 20,000 pulsars,
Okay.
and flux limited survey may not be a problem at all, especially kind of 100 parsec you are interested in.
Mm.
So anything that points towards us, we will pick it up.
Okay.
And that's where the story begins. And then other things will be online by 2030. So
Right.
I just follow up of this dark neutron. I've been not. So can I consider them as some sort of a scalar field if they exist?
So people think of scalar. At that point, I wouldn't call it a dark neutron. I would call it a dark particle carrying baryon number. People
Okay.
think of that also, yes.
Okay.
But for me, it's a
Yeah,
it's a
because
fermion.
if the good thing about is that if such dark matters are there,
Yes.
and they can actually give a dipole moment to binaries,
Okay.
which we don't expect in many of these, and that can actually put constraint by, pulsar timing, gravitational wave emission, because that's quadrupolar, this is dipole.
Uh-huh.
We have means of
Yes,
doing
yes,
that in
yes,
the
yes.
coming experiments.
I know what you mean. Yes,
Yeah.
yes. But yes.
That's all. Thanks.
Okay, I think in the interest of time, and Shorendra is waiting for you right there.
Okay.
We will conclude the colloquium right here, and we will go for snacks outside.
Great. Okay.
So let's give a big round of applause to Nirmal for a fantastic talk. It was a very nice colloquium. Thank you.
Thank you.
Thank you very much.
Thanks for being so interactive.
Yeah.
Okay, 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 go for it. Yes, but thanks so much. Thanks so much for hosting me again.
Slightly.
Okay, So my wife lands at 10 or 11.
Okay, so you can,
Yeah, at around breakfast time or something.
I will.
Okay.
Yeah.
Okay, fantastic. I'll keep it open on that. But anyway, thanks.
Okay, let's go.
Okay.
Well, this is fantastic.
Okay.